All right. Hey, everybody. We are doing support vector machines today. It's a group of classification algorithms. The last one that we're going to hit for the phase. We're going to do a little bit more classification next phase, but those we get into like neural networks and stuff. So that's for later. What I was saying right before this recording began is I have updated the calendar with office hours topics. So our office hours next week, I have some specific things to talk about. I want to talk about EDA and smoked. I'm going to talk about pickles in a data science sense. And then I do want to talk a little bit about presentation. I haven't updated the title yet, but every office hour will have something to talk about. And then a week from today, you will be presenting your projects. Again, these presentations don't have to be your final models, but just to get these out of the way. Cool, before we get into phase 4. Again, reminder, still a few of you have not done your blogs, so I'm still waiting on that. And there's still a couple more of you who haven't seen functions from yet. So whenever those are done, please send them over, because that function will truly make this project process a lot more streamlined, a lot easier to work through. Okay, let's just get into support vector machines. Any questions, as you all know, interrupt me at any time. Okay, so support vector machines is kind of like an umbrella term for this bunch of classifiers that we're going to talk about. So we're going to first talk about support vector classifier. And I guess in terms of terminology, how it works is if you have a support vector classifier with different hyperparameters of kernels, which we'll talk about in a little bit, those will all be called support vector machines. There's also a regression counterpart to this, which it's just called support. Sorry about that.
Again, it's only if that's for the fire alarm speakers in the building. Again, only if that's for the fire alarm speakers in the building. Please disregard any sounds that you hear at this time. Once again,
sorry, this is great timing for the testing. Okay. Hopefully that doesn't happen again. What was I saying? All right, we'll talk about terminology more later. Okay. The whole idea of support vector machines, let me just put these on so it's not distracting. All right, if it becomes hard to hear someone, just let me know. But okay, so the whole idea of support vector classifier, if you want to think about it conceptually, is when you have your data in space, you just want to separate your data with a plane. So imagine in the 3D space, I have a bunch of points on this side, a bunch of points at this side. Support vector classifier, what it does is it generates a plane to separate your data, and then just depending on whichever side of the plane your data point falls on, that will be the classification. Of course, not all the time you can perfectly separate your data. Sorry. All right. It's not all the time that you can perfectly separate your data in space. And we'll talk about ways that, the algorithm gets around that. Okay, so that's how SVMs work. We try and find a plane that separates the classes in feature space. If we can't, we do one of two things. One, we soften what we mean by separating. And also we enlarge this feature space so that separation is possible. And how we go about that, we'll talk about that later. Okay, so this is a great quote from the book that I hyperlinked on our homeroom. Support vector machines are sometimes used as a general method that incorporate maximal margin classifiers, support vector classifiers, etc. However, strictly by definition, support vector machine is a support vector classifier utilized with a nonlinear kernel. So what these kernels are, we'll talk about in a little bit.
Testing, 1, 2, 1, 2, testing, 1, 2, 1, 2. Maybe this concludes our test of the fire alarm speakers throughout the building. Once again, this concludes our test of the fire alarm speakers throughout the building.
I know.
Any future alarm signals,
I know.
follow normal evacuation procedures.
Of all the hours in the day, they choose the exact hour where I have to do a study. Oh well. Okay. Now that is done. So when I was talking about terminology earlier, when you have a support vector classifier, that's kind of like the simplest version of a support vector machine, is combined with a nonlinear kernel. We'll talk about that later. The resulting classifier is a support vector machine. So support vector classifier, when you change the kernel to be nonlinear, becomes a support vector machine. Okay, Cool. So we're talking about creating hyperplanes that divide our data points in feature space. Mathematically, this is a definition of a hyperplane. You can see that it looks kind of similar to our linear regression equation. You have some sort of intercept of a starting point, and then it's pretty much betas and x's. Now, you'll have the number of betas and x's as you have number of features, very similar as your linear regression equation, but because we have it set to equal to 0, it in n-dimensional feature space, just think of it as like a flat surface, or it can be a curvy surface, just a surface that divides your data. And that's a hyperplane. So an example of a hyperplane in 2-dimensional space, let's just say all of our blue dots are one class, purple dots are another class. This line perfectly separates our data. And this line, if it's in 2D, is a hyperplane.
Yeah, as I only had the linear.
So yeah, what was I saying? A hyperplane always has one less dimension than the number of features that you have. So in 2D space, this hyperplane is only a one-dimensional line. All right, so that is a hyperplane. Cool. So the simplest form of an SVM is a maximal margin classifier. Now, a maximal margin classifier is the simplest form of an SVM, and it tackles the problem directly in the sense that it doesn't compute a probabilistic model. Instead, it constructs a hyperplane to directly separate the classes. With this as an example, with this data set as an example, these are all possible hyperplanes to divide this data perfectly, right? If we have either of these 3 lines, you'll have a classifier that can perfectly classify your training data. And then how do we decide which the best plane is? So the problem with this approach is we can come up with an infinite number of hyperplanes such that we can tilt the line back and forth and it would still serve the same purpose. Therefore, we're choosing a hyperplane that would be the furthest from training observations from either side. Intuition behind it is that if we choose a hyperplane that's far from training observations, it would be far from testing observations as well. Now, what does far from training observations mean? Very, very similar actually to when we were doing our linear regression and our RMSE. We wanted to reduce RMSE, but here we want to increase the distance between point and hyperplane as much as possible. And I'm going to illustrate real quick how that is done. So given this example over here, we have our training observations and we have our hyperplane. Now they chose this line over here. And that's because if we were to measure the distance from point to line, and when you measure distance from point to line, it's always like a 90-degree angle. It always has to be a 90-degree angle. If not, I could measure distance like that, and that doesn't count. But if we were to measure all of these distances with different hyperplanes, this hyperplane maximizes the distance. When you maximize this distance, it means that the hyperplane has, I guess, more leeway for data points that are perhaps like over here. If a data point is like right over here, it'll still be classified correctly. And the same thing on the other side. So that's how it decides. That's the gradient descent process. It just adjusts the hyperparameters, not hyperparameters. It adjusts the parameters of the hyperplane to best fit the plane in between the classes. Questions about this? This is pretty much the entire intuition of support vector classifiers and support vector machines. All right. Okay. So this distance between training observations, let me clear this. The distance between training observations and the hyperplane is called the margin. And the classifier aims to find the maximal margin from the hyperplane that separates the training examples. So given this example, the margin is just defined as the shortest distance between points in the line. So for this case, this would be the margin. So we want to get the largest margin possible, which is basically plus minus from the hyperplane area where there are no data points. Cool. So how do we construct this? How do we do this gradient descent process? It's very, very similar to the gradient descent process for linear regression, where you're pretty much taking the line, instead of getting to best fit the data, now we're taking the line to best separate the data. And each of these lines, well, each of these hyperplanes is going to have an equation with, a bunch of betas, and that's what the gradient descent is working on optimizing. Cool. So we're maximizing this subject to this. This is basically some constraints for mathematical definition of a hyperplane. And we are trying to maximize this margin as much as possible. And yeah, you can actually find the computation for this optimization problem if you're interested. Okay, so that is the simplest form of a support vector machine, the maximal margin classifier. Now, even though it sounds very, very intuitive for making a classification problem, for solving a classification problem to just build this margin, it might not be desirable under two circumstances. One, it will be very, very sensitive to individual training observations, right? Let's say you have one purple point that is maybe over, let's just say that this guy, oops, I want to draw it. So let's just say that we have like a purple data point that's all the way over here. That can really change where the hyperplane is formed, because now this distance is going to try and shift the line such that it looks more like that, I guess. Also, the algorithm will not converge if the training observations cannot be linearly separated. Now, what linear separation means that we can literally draw a straight line or a straight plane through your data. That's what it means by being linearly separable. So the algorithm for a maximal margin classifier actually will not be able to solve itself if your data cannot be perfectly split up. And in a lot of real life data, that is the case. You can rarely perfectly separate your classes in your training data. So therefore, what can we do? We use something called a soft margin classifier, basically give it a little bit more leeway for things that are outliers or maybe, yeah, pretty much outliers, or basically decrease the sensitivity to data. All right, so take this example to start. With this example, it looks like we can't really linearly separate our data. So therefore, we're going to use a soft margin. So rather than seeking the largest possible margin so that every observation is not only on the correct side of the hyperplane, but also on the correct side of the margin, we allow some observations to be on the incorrect side of the margin, even on the incorrect side of the hyperplane. So there are two boundaries we're talking about here. We have the hyperplane and we have its margin. So in this scenario, when we're using soft margin, if we say this is the blue side, let me just draw this. Let's just say this is the blue side and this is the purple side. Excuse my ugly scribbles. Data points can end up falling to the opposite margin. So in this case, this point number 12 over here is pretty much right on the opposing side's margin. And this point 11, pretty much any purple point can go up to this line over here. So that's how soft margin is constructed. Of course, that is also taken into account when you're calculating your gradient descent and your cost function, because when something's on the wrong side of the margin, your cost function does get penalized as well. But this just makes it such that your algorithm can converge with some margin. So some very similar formulas. I'm not going to go through all of the math, but it's very, very similar. The only thing that instead of having this being just a strict margin M, this you have the margin plus, hyperplane being M, you have some margin of is that epsilon? I always forget. Yeah, mini epsilon, which is the margin basically. Cool. So hyperparameter E, epsilon, I think it's epsilon, yeah, is known as the slack variables, and that determines how wide you allow your margin to be. So this can be also used to control for regularization. If you want a wider margin, you actually overfit less. If you have a stricter margin, you overfit more. Cool. So this value C, the value of your margin, is the sum of the margin over all of the training observations. And it does, as I've just mentioned, control the bias variance trade-off of the statistical technique. So high value of C means we're more tolerant of the violation, which will give us a model with high bias, low variance, but a low value of C gives us more variance, less bias. So examples, this is a very underfit model. This is a potentially overfitting model. So smaller margins, more potential to overfit. In scikit-learn, when you have an SVM, pull up the SVM. No, this is regressor. So let's find, do we have the classifier? All right, scikit-learn, SVC. There we go. Okay, so this is the method for support vector machines, and as you can see here, C is your regularization parameter, your margin. Cool. Awesome. So any questions at this point? We've talked about the maximal margin classifier, which we're just trying to build the best line that separates. And then we talked about soft margin classifier, one that introduces the ability to have points on the wrong side of the hyperplane. Cool. All right, so building up on that, we have support vector machines, which is basically a support vector classifier with a non-linear kernel. We haven't talked about kernels yet, and we will. But the kernel trick is something that we actually use to transform our data. Earlier at the start of this, we talked about two methods that we use for SVMs. We talked about this already. We softened what we mean by separates. That's when we brought in our margins, our soft margins. And then next, we're going to enlarge the feature space so that separation is possible. Now, this is the kernel trick. Mathematically, very, very complicated. I've seen some like formulas for doing kernel tricks. It's very, very intense. I myself haven't even gone into like break down all of those equations, but conceptually, we'll see what it is. So imagine we have data like this. Sometimes we have this training data that can't be separated even with the softened margin, right? If we're given a data set that looks like this, how will we even begin to classify? Of course, if we have a different model, like, I don't know, maybe decision trees or something, maybe you can like segment your data such that it looks something like that, and then you can classify like that. But it doesn't work for SVM because SVM is literally trying to fit something to separate your data in its feature space. So with an SVM, if you just have your data looking like this, it's not possible. So that's when we employ the kernel trick to enlarge or change our feature space. One picture example to show what's happening. Let's just imagine we have this data that looks like this. What the kernel trick is doing is it looks for different ways that we can better separate our two classes if we were to take some combinations of features. And what it does is it can transform something that looks like this in 2D. And a quick example, it turns this 2D data into 3D data. It basically figures out, okay, everything maybe they like draw a circle around here. Everything within the circle will be one level, above the circle will be another level. We can create this 3D space. We're enlarging the feature space so that in this new space, we can pretty much cut through, we can fit a hyperplane through these two classes. Of course, this is a very clean example. It's never this clean, but the whole idea of a kernel trick is to think of ways that we can expand the feature space, maybe representing our feature space as like a weird combination of other features, maybe making a new feature that is, I don't know, some polynomial combination of other features, just so that we can try and create this separation. And you don't have to worry about doing this because it is very mathematically complex, but just trust that the algorithm based on what kernel you use is going to employ a bunch of different methods to try and create this separation between your data so that then it can fit a hyperplane through your data to classify. Questions about the kernel trick before I get into more details? The whole intuition is this cannot be linearly separated. We increase the number of dimensions so that it can be linearly separated. Cool. Awesome. So some things to mention. We enlarge the feature space through the use of a kernel. So the kernel is basically what takes the data from this to this. Next, we're going to fit a support vector classifier in the enlarged space. So in this enlarged space with these two layers, imagine we're going to fit a hyperplane between the two rings. If we transform it back to original space, pretty much you can guess that the decision boundary is going to look, I cannot draw this properly, but imagine a decision boundary would probably look something like that, where everything inside the purple circle is going to be blue, everything outside the purple circle is going to be red. So that allows for non-linear hyperplanes, or is that even called a hyperplane? I forget. But it's basically, it allows for non-linear decision boundaries. boundaries. So yeah, it results in nonlinear decision boundaries in the original space. But what was happening is we enlarge the feature space, create a linear hyperplane, and then put it back together. So therefore the linear hyperplane becomes nonlinear in the original space. Cool. Questions about that? Awesome. Okay, so how is this space or how is the kernel trick being done? It's basically by looking at the relationships between your data points to see how it could possibly look for separation. I'm not going to go into too much detail regarding this part, but basically what it's doing is it's computing the inner product of all observations with each other. It's basically looking at sort of you can sort of think of it as like the difference in observations, is looking for differences in observations so that it can generate new dimensions that will nicely separate them. And it does that by way of inner product. And what inner product is imagine you have 2 data points and you have 2 data points, 10 columns each. The inner product is basically defined by the dot product, which we talked about when we did linear algebra. But let's just say we had, let's go down to this. Let's just say we had these 2 rows over here. The inner product is basically this times this, plus this times this, plus this times this, plus this times this, which results in a number that your algorithm will eventually use to help generate the new dimensions in the kernel trick. So yeah, there are many different kinds of kernels. I would say that in SVM, I think they mentioned a few. There's linear kernel, and if you use a linear kernel, your SVM is just an SVC. There's polynomial, RBF. RBF, I think, is radial, sigmoid kernel, and pre-computed. Pre-computed, I forgot. I don't know if that's something that you have to do, but the most commonly used kernels are polynomial, radial, and sigmoid. And usually what you would do is just try all 3 and see which one works better. In a little bit, we'll talk about when it is best appropriate to use SVMs or SVCs. Okay, so with these different kernels, you can see that the functions look slightly different. What these mean, I'm not going to go into because it's not important for right now. Okay, so to implement, as we know, exactly the same. Again, we have this random CSV, we have variance, skewness, kurtosis, and entropy of banknotes, I guess. We're going to do our train test split. We instantiate, fit, predict. We can see our runtime. That is an okay runtime. And then we get our metrics as before. Things to note about support vector machines. I guess let's talk about some pros and cons first. It's pretty effective. Typically, you have good results out of support vector machines. However, it is not interpretable. You can't get coefficients. You can't get feature importances. It's very hard to learn things about your data set through an SVM. The optimization is hard to understand. As you know, it's not only just as simple as fitting a plane. Of course, in an SVC example, it is just that. But once you get into the kernel trick, it becomes very, very difficult to interpret. And a situation where SVMs work really well is when you have high dimensional data sets with low amount of observations. High dimensional means that you have a lot of features, fewer rows. When you have a lot of features, it just means that it has more space to try and fit a plane through the data. So therefore, just intuitively, it works better. And if you have relatively lower amount of observations, SVMs will typically perform better versus other algorithms. Now to think about computational complexity. SVMs typically take longer to run than other models because, and this is especially if you use a nonlinear kernel, because one is doing the kernel trick, which in itself, it's doing its own procedures of figuring out what the best way to increase the dimensionality of your data. So that in itself takes it's a very, very long process. And then after that, you still have to fit a plane through that enlarged data set. So it's doing a lot of things. SVMs therefore take a very long time to run. In the next phase, I think is the second topic in the next phase, we're going to introduce something called PCA, Principal Components Analysis, which don't worry about it for now. But what PCA does, PCA is actually used hand in hand with SVMs quite a lot. What PCA does, PCA actually reduces the dimensionality of your data so that it reduces the dimensionality of your data while still maintaining as much separation as possible. So that when you take that data and put it into an SVM, it has less work to do. But we'll talk about that next phase. If anyone's curious about what that is, we can talk about it during 101s, but I don't expect anyone to be using that this phase. But yeah, that's SVMs. That is our last classification algorithm for this phase. Any questions or thoughts or anything? Cool. Well, with that, implementation exactly the same. I will say that now that we've gone through all of our classification algorithms, I do want to reiterate that for this phase, I don't expect you all to have like a super deep understanding of every model, but when you're working on your project, whichever model you end up picking as your final model, or maybe just one that you like a lot, just pick one to learn for now. I think, yeah, just getting one out of the bag, that'll be good. Cool. All right, well, if there are no questions, I'll stop the recording over here and we will get into our check-in.